So today we'll be discussing some questions which are from the week 9 content, where you discuss some more popular deep learning architectures, and you're saying something. Smita, are you saying something? Or you left your mic on by mistake? Hello Smita, are you saying something? Your voice is not clearly audible. You can type in the chat. Is my voice audible? Okay, I think you were not saying. Okay, so what I was saying is, in the week 9 we discussed uh, some more popular architectures like this GoogleNet and different optimization algorithms like gradient descent based algorithms, which are used for tuning the model parameters, various properties of these algorithms, which are popularly used in for training deep learning models. So let's look at the first question. If you have any doubts, then just interrupt me. You can unmute and speak or type in the chat. Any doubt from what we're discussing today, or from the lecture, or anything that we discussed in the previous uh, live sessions. So the first question is asking, what is the main purpose of auxiliary classifiers in GoogleNet? So GoogleNet was the architecture which sort of was the state of the art in that image classification competition. So in 2014, I think, and the Google Ad architecture was sort of very long, where you had a classification layer. Here there was a classification layer fully connected, and then again here you had a classification layer, and here also you had a classification layer. So basically, the inputs from here you are classifying into your respective classes. The inputs from here also you are classifying. Maybe I'll just get the architecture image. Google Net architecture. Yeah. Yeah. So this is the architecture, and we are asked what is the use of main purpose of auxiliary classifiers. So the auxiliary classifiers are these extra classifiers that you have. So in the previous models that we saw, we had one classification sort of layer in the final layer of the deep learning model, which gives you the labels as to the image belongs to which of the classes. Now here we have some uh, like classification layers in the intermediate part of the neural network, and this will also predict the same thing. So then what is the use? The use is when you're training the model, uh, when you backpropagate based on the loss that you get from the final output layer labels. When you compute the loss, when you backpropagate, as the gradient reaches the initial layers, it may become very low. That is the vanishing gradient problem. So to avoid that, you sort of introduce these auxiliary classifiers which try to classify based on the intermediate representations. So the loss from here will be backpropagated, so these layers will not face vanishing gradient again. Here also you backpropagate the loss based on the output of this part. So these parts will not have zero gradients. So then what is the main purpose? The main purpose is to avoid the vanishing gradient problem. So if you look at, so this is the correct answer. If you look at the other options, it is saying to increase the number of parameters. I mean, yeah, if you add more such auxiliary classifiers, the number of parameters do increase, but that is not the purpose for which they are introduced. That is sort of a consequence. The purpose is to get rid of the vanishing gradient problem, to increase the inference speed. So there won't be any benefit to the inference speed, that is the time it takes to predict the output for a single image. That depends on how deep your neural network is. If it is very deep, then it will take a long time for the feed forward part to work, and you will get a late output. So the auxiliary classifier doesn't have such a role in increasing the inference speed. So we can safely say this B is the correct answer to avoid the vanishing gradient problem. So trying to ensure like the intermediate representations, they are also able to classify. So we should expect that the loss at this final classifier is the least, while these two classifiers may have higher losses. This one having higher loss than this one. I mean, the deeper the auxiliary classifier is positioned at, the less its losses. Okay. Any doubts in this question? So to solve this question, what we had to know was we had to know this Google Net architecture and the fact that there are auxiliary classifiers which are there in between here. We had to know what is the vanishing gradient problem which deep neural networks face. So then we have the idea that these auxiliary classifiers are introduced to avoid the vanishing gradient problem. So there is no doubt in this part, then I can go to the next question. Which of the following is an innovation introduced in the GoogleNet architecture? So this is multiple select question. There are you can have multiple correct answers. So first thing is one cross one convolutions to reduce the dimension ReLU activation function, dropout regularization, use of different size filters for the same input. So this is sort of a historical sort of fact that what this Golang architecture introduced, which resulted in it performing better than all the other models in the image classification task. Let me just paste that figure here again. So if you remember from the lectures, you had sort of these parts. I think you can say this section. It is called the inception module. It's only this part. This is the inception module. So in this inception module, what you have is you have these 1x1 convolutions, and you have the same input is given to multiple sort of kernels of different sizes. Multiple filters of different sizes are converted to the same input. So so what is the innovation introduced in Google and architecture will be this 1x1 convolutions to reduce the dimension. That is this part. And use of different filter sizes for the same input. That is this part. So if you look at the other architectures like AlexNet or something, here if you see, you convolve this image with this one filter, you get this image. Then you convolve it with some filter and you get this, and you keep using different sort of filters to add different stages. And if you look at LayNet, I think that also has same kind of thing. You have 5x5 convolution, again 5x5 convolution, and do it one after the other. So this was something different that was done by the Google sort of team. Yeah, you have a question? Srinidhi, you having a question? Okay. I think you have raised your hand in this, so that's why I asked. Okay. So this railway activation was introduced much before, and dropout was also introduced much before. So these were the two things which came with the Google Net architecture. So any doubts in this? I'll go to the next question then. Select the parameter of vanilla gradient descent controls the step size in the direction of the gradient. So I think they're saying select the parameter of vanilla gradient descent that controls the step size in the direction of the gradient. So vanilla gradient descent, how it works is you have your Wt plus 1, which is equal to Wt minus eta times the gradient with respect to W. This is your cost function. J is your cost function, not your loss function. So the step size and direction of gradient. So this is your gradient, and this is your step size. So how much times the gradient you want to modify your parameter. And this is also called learning rate. Because if your learning rate is too small, then your parameters will be updated by there will be a small change in your parameters W of your deep learning model. So when the change is very small, but like if you start from some W1 and your optimal parameters are W star, so if you take very small steps towards your W star, so it will take a long time. That means your learning rate is very low. If your learning rate is very high, then what can happen is you may miss this W star. We may reach somewhere here, then you will have to come back here like that and keep doing till you reach W star. This is when learning rate is high. So the parameter that controls the step size and direction of gradient is learning rate. Momentum is different, right? What we did in momentum optimizer was you look at in which direction your past gradient sort of happened. So in momentum you have that term, right? You have this term Vt is equal to gamma times Et minus 1, this is the momentum optimizer, plus eta gradient, right? So Wt plus 1 is Wt minus Vt. So I think this is the gamma that is referred here. So first of all, this is not the vanilla gradient descent. Vanilla gradient descent is this. And here you don't have momentum or gamma. You only have this eta, which is step size or learning rate. In the momentum based optimizer, you have this gamma term, and this gamma times Vt minus 1 is your sort of momentum, or Vt minus 1 is your momentum. And gamma is sort of how much of the momentum you wanted to take into account into the direction that you're going to decide. So for this question, what we wanted to know was what is the vanilla gradient descent update step and which term is the learning rate or step size in it. So that's a simple question. Any doubts? Okay. So let's look at this question. Suppose Elena has trained a neural network 3 times, experiment A, B, and C, with some unknown optimizer. Each time she has kept all other hyperparameters same, but changed only one hyperparameter. So in these 3 experiments, one hyperparameter has been changed while training a neural network. From the 3 given loss curves, can you identify what is the hyperparameter? What is that hyperparameter? So we have to identify what is the hyperparameter that was changed in these 3 experiments. So x-axis is number of iterations, y-axis is loss. So maybe it's the training loss, we can assume. So if we look at these 3 plots, what is changing is in the first plot, like you're starting from sort of the same loss, which is a high value like 10, and then the loss is decreasing around 4, and then it's becoming stable. And the fourth, around from the fourth iteration onwards, it becomes sort of straight, and that is what we are observing in all the places. The only change is how jittery it is. Here, if you see, it is a lot more jitter is there. Here it is less, and here it is very smooth. So the options given are batch size, learning rate, number of hidden layers, loss function. So if you change the batch size, if you change the batch size, what will happen is if you are using batch size of 1, then it will cause a lot of jitter because you are basically doing stochastic gradient descent. So if you like for each sample xi, you only look at the loss for this sample, you find the gradient with respect to this sample, and you update your parameter with respect to xi. So as you keep doing it for each of the sample, it may not be in accordance with the whole training set, which is from my which has some n samples. So for each sample, it may adjust the weight till it reaches a global optimum or local optimum for all of the samples, where the gradient is not changing much for all of the samples at this point. And when I increase the batch size, then my jitter will decrease. And if I use the entire n samples to compute the gradient, then it will be the most smooth one. However, if you observe one thing, that uh, in all of the cases, it, it becomes straight after 4 iterations. So that is not necessary to happen if you change the batch size. If you change the batch size, the time to converge with bigger batch size may be less, while the time to converge for a smaller batch size may take a lot of time. Like this may take a lot of time as compared to this. However, it may also happen that uh, they are the same. So we can't really say, we can't discard this option. But let's look at the other options. B is like changing learning rate. So if you change the learning rate, then definitely this should change. Like it may become something like this for a smaller learning rate. For a higher learning rate, it may become something like this. This can be for a higher learning rate. So the time to converge will change if you change the learning rate. But in this cases, what we see is the learning like that it converges almost around the same iteration, that is at 4. So we can discard the learning rate option. The number of hidden layers. So if we increase the number of hidden layers, that means we have more parameters to tune. That means it will take more time for it to converge. So the same thing will happen. Like it won't converge, everyone might not converge at 4 iterations. So this also we can discard. So if I increase layers, increase parameters, that means more time to converge. But your time to converge is same. If I change the loss function, then these values should sort of differ, because everywhere we are seeing it is from 0 to 10. For different loss function, this should this can change to something very higher or something like that, depending on your loss function. So it doesn't seem like the loss function has changed. So this also we can discard. So I guess A is the correct answer, because we are seeing the effect of changing batch size. If you are using the entire training data, then it will be smoother. If you decrease the batch size, you will have more jitter. If you keep decreasing it more, then the jitter will increase. Okay. So what we sort of had to know is how changing different hyperparameters changes your like loss, the training loss curve, or the dynamics of learning, how it is affected by different parameters. You mostly have to have a sort of intuitive understanding at a beginner level, and for most practical purposes also that is sufficient. But there are theoretical results also which one can look at if one is highly interested. So any doubts in this part? So the difference was we are looking at the entire data at once, computing the gradient, updating the parameter. Here we are looking at small samples at a time, updating the gradient, updating the parameters, computing the gradient, updating the parameters. Here sort of we are looking at very few samples, one or two, and updating the gradient and computing the gradient and updating the parameter. So it will oscillate a lot. Okay, I'll go to the next question. We are training a neural network using a normal gradient descent algorithm. We observe that the change in weights is small in successive iterations. What are the possible causes for the following phenomena? So there are multiple correct answers. So what they are saying is you're updating your parameter based on normal gradient descent, which is eta times now they are saying wt change in weights, that is wt plus 1 minus wt, and this is small close to 0. That means this value eta this is close to 0, right? So this means either eta is small or this gradient value is small. So that is what we have in our options, right? I think this is the gradient of the gradient with respect to w. So eta is small or gradient is small. That is this option. So that is using a normal gradient descent. Change in weight is small in successive iteration. That is wt plus 1 minus wt is small. That means this part is also small. That is what I have written here. That means either this or both can be small. And that is exactly what is there in the options. This is gradient with respect to w. That is small. And eta is small. So any doubts in this? Okay, then I'll go to the next question. If we start the gradient descent from point C, which of the following is most likely to be true? So C is a point here. This is our C point. And if we are using gradient descent from this point, which is most likely to be true? So gradient descent means you will come, this is your sort of loss curve. Okay, you can say this is your lost value cost function, and this is a w. Let's say there is only one parameter w, let's suppose. Then this direction gives me slope at this point is this, which is gradient with respect to w at this C point, WC. Now this is the negative direction. This is the step that you will take eta times. So that means it will go somewhere here. So you'll reach some point here, and then you'll keep doing like that the descent step, and you'll reach somewhere here where the gradient will become 0. So if we start gradient descent from point C, which of these options will be true? Algorithm will converge to A dash. So it won't converge to A dash, right? Because our gradient is in the opposite direction, so we have converged at B dash. So A is false. Algorithm will converge to B dash. Yeah, that is true. So this B is true. Algorithm will converge to B. And this can also happen, but it will be very sort of rare if you take a step. Like if you adjust your learning rate in such a way that when you take a step, it directly reaches at this point where the slope is 0. So usually you stop your gradient descent algorithm when you reach slope 0. If you directly shortly take one step and you adjust the learning rate such that you exactly reach this point where the gradient is 0 and you stop there, that is the only case when you reach, you'll converge at B. If you reach somewhere here also, then again you will do gradient descent and you'll reach back here. Only if you reach exactly at this point will you stop. So that is a very rare phenomenon. So we can discard this because it is saying most likely. This is like very less likely. Algorithm will not converge and oscillate around A dash. So that is also very less likely. It can happen if you take let's say you take a big step and you took some step in this direction, you reached here, and then you took again a big step and you reached here. And now because your learning rate is high, you may sort of oscillate like this or something like that. You may oscillate if your step size is too big or a certain, if it is a certain range, that may happen. But that is also what is asked is what is most likely. So most likely seems it will converge at B dash. This is also very less likely sort of situation. So I can discard D. The chances are like your learning rate will have to be in a very well defined range, and you will have to know the dynamics of this loss curve to sort of for this to sort of happen. Okay. So any doubts in this? I'll go to the next question then. So there are two statements and we have to say which are true, which is true and which is false. First statement is mini batch gradient descent will always overshoot the optimum point even with a lower learning rate value. So here if you see what it is saying, minimized gradient descent will always overshoot optimum point even with a lower learning rate. So that doesn't really make sense, right? Because usually when you have higher learning rate is when you overshoot your optimum point. And this is like a very complex, not complex, but here they are saying it will shortly overshoot the optimum point even with lower learning rate. So we have no reason to sort of uh, feel that it should happen this way. So we can say statement 1 is false. Now let's look at, so this is false we can say. Let's look at statement 2. Mini batch gradient might oscillate in its path towards convergence and oscillation can reduced by momentum optimizer. So definitely minimal gradient descent might oscillate. I mean if you have here we just saw in This sort of example, when you have mini batches, there are oscillations. There is oscillation. Now the other part of the statement was the oscillation can be reduced by a momentum optimizer. So in momentum optimizer, what happens is, let's say this is your like the contour plot of your loss. This is a parameter. So normal gradient descent may be something. Start from here. And it may be something like this. Something like this may happen. Okay. And in momentum, what will happen is, because you have, when you are going, the gradient is in this direction, but you have momentum towards here, sort of. That is what at this point, when you took on this step, you say you have momentum which is in this direction. Let me have this. You have momentum in this direction, so that's why you add this plus this and you take a step, sort of take a step here, then you here take a step here, and then you will reach here. So because of the momentum thing, this I am talking about the momentum direction. Because of the momentum, the oscillations may be less, is what I was trying to say. The momentum doesn't allow it to deviate from the direction it is moving too much. So the oscillations, or the momentum, sort of reduces the oscillation. Okay. So the correct option is statement 1 is false. So we can say this is sort of possible statement. So statement 1 is false and 2 is true. So what happens in the momentum, I had written the formula right sometime back. This is the momentum optimizer. So if you are looking at this, what you see is, you compute this weight update is based on the direction of the previous weight update plus the gradient at the current WT. So the previous direction of previous update is what is your momentum. That means it depends on the previous weight update term, where you might have used a different batch. So each update you are using a different sort of mini batch. So the momentum of the previous mini batch is used in the update for the current mini batch. So that file, it will reduce the sort of oscillations, because the gradients sort of generalize well for your data. While in the regular gradient descent, like regular minimized gradient descent, each update is independent of the previous batch update. But the previous batch update is sort of carried by the momentum term. So that's why it doesn't oscillate too much. So it's sort of a very intuitive explanation that I'm giving. But I hope it makes sense. If you have any doubt, then please ask. So here you'll be having one more term. So x, let's say it is x t corresponding to mini batch at time or iteration t. Okay. So what we had to know here was, when does the, and there are two statements here. One is talking about overshooting the optimum point when the learning rate is low. So, so I think we have seen in the this example, if my learning rate is small, then I'll keep taking small steps, take small steps, and I'll reach my local optima. Only if my learning rate is high will I overshoot the local optima and reach somewhere here. So it's lower learning rate, I'm not likely to overshoot. Here it is saying it will always overshoot, but it is very less likely that I will overshoot the optimum point. So statement 1 is false. Statement 2, it is talking about the oscillation that happens when you are using minimized gradient descent. So by introducing the momentum term, the oscillation sort of reduce. So you need to understand in this part is what is this momentum term, what is the role it is playing. At v0 you can assume it is 0. So then v1 will be uh, gamma into 0 into eta times or w1 gradient at time step 1 and the mini batch at time step 1. Like that, if you keep doing, what you will get is, I think at vt I have written that thing, gamma t minus 1 eta times so until gamma power 0, that is 1. So at time t, the momentum is carrying the gradient information, or sort of the momentum from all the previous mini batch updates that has happened till time t. So that's why the oscillation is sort of less. Okay. Okay, then I'll go to the next question. Which step does Nesterov accelerated gradient descent perform before finding the update size? Increase the momentum, estimate the next position of parameters, adjust learning rate, decrease the step size. So the Nesterov update, uh, it is the modification of the momentum based optimizer that we just saw. And so what you have is Wt plus 1 equal to Wt minus Vt, where this Vt is gamma Vt minus 1 plus eta times the gradient, and this W hat t is Wt minus gamma Vt minus 1. So that is we are currently at Wt, and we want to update our parameter W at the current time step t. So what we do is we take a step in the direction of our current momentum to compute W hat t, and with respect to this W hat t you compute the gradient, and this is the Nesterov. So in the previous momentum based thing you are computing the gradient at Wt, but here instead of doing it at Wt you are using this sort of look ahead step, look ahead gradient. And based on that gradient and the current momentum you decide your update step Vt, which you use to update your parameter. So before finding the update size, it is what it is doing, it is estimating the next position of parameters. That is what is this, right? This is an estimate of the next position of parameters. I think I should, instead of Wt I should use W hat t plus 1 to imply that it is the next position estimate. Okay. So if you have something like this, you are at this point, say you came from here, so you have momentum sort of towards this direction, and you take a step further in this direction and look at the gradient there. So then this is the sum. So you take sort of direction midway between these two, which will be something like here. So this is your update step, Vt. This is gamma 1. This is Vt minus 1, and this is gradient. Okay. So the step that you are doing before the update is not exactly increasing the momentum, and it is not adjusting the learning rate or decreasing the step size. It has nothing to do with eta. You are estimating the next position of parameters via this step, the look ahead gradient step. So any doubts in this part? Okay. So here they are saying we are training a neural network and are at iteration T of 8 updates with weight Wt. Suppose using the momentum based algorithm we cross the local minima and get Wm t plus 1. That is, you are currently at Wt, you use the momentum based update and you reached Wm t plus 1. If from Wt we use an extra accelerated gradient, we get Wn t plus 1. So if you are using an extra accelerated gradient, you get Wn t plus 1. Then which of the following statements is true? So from Wt, the same Wt you have performed two different weight update steps and you got two different updated parameter values, Wm and Wn. And we have sort of asked like what which of these options is true. So there are all options are having inequalities, where some inequalities have the absolute value of the parameter weight value, some are having the difference, that is the how much the parameter value has changed. So this inequality, if you look at the first one, they are talking about the change in the parameter value is greater than the parameter value at some point. So that is a comparison that we can't really make, right? Because that depends on many things like learning rate, what is the parameter value at Wt. If Wt is, let's say, really big sum, 10 power 20. Then Wm t plus 1 will be some zero point 0.5 plus 10 power 20. So the difference will be zero point 0.5. But Wn can still be at somewhat in the range of 10 power 20. So then we can't say this first option. Similarly, we can't say the last option also, because these quantities can't really be compared. So we have to look at these two options. So they are talking about the change in the parameter value when you are using nested or momentum based uh, update algorithm and the nested accelerated gradient algorithm. So what was the difference in these two things? So in the momentum one you had written it, right? You can just copy it from here. This is Wm that you got, and the other is the Nestor one. So here you have Wn. So from here you got Wn. You may write this down. Wn t plus 1 equal to Wt minus Vt. Maybe I can write this momentum as m, sorry, here also m, and here it is n. Because we don't know at t minus 1 what algorithm was used, but from t to t plus 1 two different algorithms have been used to compute the weight update. So that we are sort of written here. And one more information is given to us. Using the momentum based algorithm, we cross the local minima and get WMT plus. So when you did this update, you had something like this, and from here you had something like this. You crossed and you reached here. This was your local minima. So this is WT. This is WMT plus 1. So you have crossed the local minimum and reached here. Now what can you say about when you are using Nestor or gradient descent, what will happen? So what the difference in these two is, you are doing this look ahead step. Look ahead gradient and look ahead parameter. So and that is in the direction of your momentum. So here also your update is sort of the momentum plays a role in which direction you take your update. And here also the look ahead step is based on your momentum. So you will sort of your w one second, your w hat will be in this region. So this step will tell me that uh, it will compute the gradient in sort of this direction. So when my momentum is asking me to go here and my look ahead step is asking me to go here, then I will sort of stop, take a step somewhere here, right? So this will be my w and t plus 1. So because of my look ahead step, it will again bring me like closer to my local optima. So you can say w wmt plus 1 minus wt will be greater than wnt plus 1 minus wt, because it will sort of prevent my parameter from overshooting because of the look ahead uh, parameter, the look ahead gradient that I'm computing. So that is, this will Nesterov one will be the difference in Nesterov parameter will be smaller than the momentum parameter. So it is the second option. So it is basically a comparison of their momentum values. So if they are vectors, then you can consider some norm kind of thing. So because this momentum is computed based on the look ahead parameter, this can be that step, update step will be smaller. Because this and this are in opposite direction, this term and this term. Okay. So any doubts in this part? So what we had to know was how these two algorithm updates work, and uh, this crucial look higher parameter step what it does, and this information that using the momentum optimizer you had overshooted your local optima, and because you had overshooted in the next step, the look ahead parameter computes the look ahead gradient, which will sort of prevent you from overstepping too much. And because of that, the weight update for the Nesterov gradient will be smaller in compared to the momentum based update. Okay. So for these questions, you have to sort of familiarize yourself quite well with how these algorithms are sort of created. So this question is asking which of the following are among the disadvantages of Adagrad. So the Adagrad algorithm, what it does is you have Wt plus 1 is equal to Wt minus eta times some small update plus square root Rt times your gradient at time t, and this Rt is from tau equal to 1 to t, that is till the current time step, the square of the gradient. Gt is your gradient of that mini batch. Maybe I can just write it. So what is happening in this Adagrad algorithm is as your number of iterations increase, you compute the square of the gradient for the given parameter, like you submit till the current time t. So this will be a vector if you consider w as a vector. If I have to just look at one of the this thing wt, so here if it is a vector it will be epsilon times I. So for a single value we rt ith value into the gradient ith value. The circle is the element wise product. So here, because there is only one element, you can consider direct scalar multiplication. So RIT is the sum from tau equal to 1 to t g tau I squared. So you are adding the sum of the squared gradient at each time step for that particular parameter, and as that keeps growing with time, for that parameter you are reducing the learning rate by this term. So epsilon is just a small value, so that you don't divide by 0. A small value you are adding so that there is no division by 0. So when time increases, this term will become very large, and your the scaling that you're doing to the learning rate eta by root rt, that can become very small as t increases. So what can happen is it gets stuck before reaching the minima, right? So before reaching the minima, if it is reaching too long to reach the minima, it may get stuck at some point because you started off from a far away place from your local optima. So it took you too long to reach there, and by the time you are reaching, the gradient accumulation became too high. So your learning rate got scaled to a very low value, and because of that, you can get stuck before reaching the minima. If you look at other option, it doesn't work well for sparse matrix. I mean, in sparse matrices, uh, each each of your term will be scaled differently based on the accumulated gradients, right? So we have no reason to assume that it won't work well for sparse matrix. It usually goes past the minima. So as the gradients are accumulating, the learning rate is sort of decreasing. So it won't go past the minima because you are decreasing the learning rate with increasing time steps. And the other option is weight updates are very small at the initial stages of the algorithm. At the initial stage, the gradient will be just at the first time step, let's say. So there is not much accumulation happened. So this RT uh, will be small. So it will be high. So weighted rates will be actually be larger at initial stages of the algorithm. So D is also incorrect. So the correct option is C, that it gets stuck after reaching the minima, before reaching the minima. So there are each algorithm has some parameters which are computed in certain manner and which sort of dictate the dynamics of the weight updates. So while sort of just analyzing, we can get an intuition of how each of the parameters influences the weight updates. So any doubts in this question? Okay. So again we have two statements and we have to talk about which one is false and which one is true. Apart from the learning rate, momentum optimizer has two hyperparameters, whereas Adam just has one hyperparameter in its weight update. So Adam, did we discuss Adam? So apart from learning rate, momentum has two hyperparameters. If you look at momentum, apart from learning rate, there is only one hyperparameter, right? So apart from learning rate, there is momentum has only one hyperparameter. So straight away we can see statement 1 is false, whereas Adam has just one hyperparameter in its weight update equation. In Adam, Adam optimizer, I'll just write how you have first movement and second movement computation here. First movement is beta 1 s of t minus 1 plus 1 minus beta 1 gt. So this beta 1 some value between 0 to 1, and this is your first order moment. And then you have rt is beta 2 rt minus 1 plus 1 minus beta 2 gt. This is your second order moment. Beta 2 is also in 0 to 1, and you do a bias correction here. Where st is st hat st upon 1 minus beta 1, and rt is and your weight update is wt minus so it is sort of the ratio of the first moment and the square root of the second moment. And you have three parameters, beta 1, beta 2 and eta, and this epsilon is a very small value, just which you keep to avoid division by 0. So you can say the statement 1 is false because in Adam also you have a lot of parameters to tune. Adam optimizer and stochastic gradient doesn't have the same weight update rule, so that is also false. We see like there is a complex weight update rule. So this term, it has the gradient information here, and this is the deviation start off. So it is a combination of the momentum and this RMS prop algorithm. I think RMS prop question we haven't come across yet. So this weight update seems a little bit more involved, where uh, you are accumulating the gradient in the previous one. That was this was Adagrad, right? In Adagrad, you are accumulating the gradients by summing it till time t in this form. But here, the way you are accumulating is you are accumulating in RT, where you are giving a factor as to how much you want to accumulate from the previous step and how much you want to accumulate the gradient from the current step. So we can do 0.5, 0.5 or 0.1, 0.9, something like that. Beta 2 plus 1 minus beta 2 is 1. So you're taking some fraction from the previous times, like sort of updates, and some from the current. And the same thing you're doing with the gradient also. So you can say this st minus 1 is kind of the momentum. So here statement 1 and statement 2 both are false. So in this question you had to know, I mean this was sort of simple because they're talking about how many parameters are there, and by just looking at the formula we know that there are more parameters than what is mentioned here, and the weight update rule is drastically different from normal stochastic gradient descent. Okay, so I'll go to the next question. Which of the following is correct property of RMS prop optimizer? So I'll just write. So that is what I discussed in the last question, that Adam is a combination of RMS prop and the momentum optimizer. And I'll just write how the RMS prop is. So here Vt is equal to beta times Vt minus 1. So 1 minus beta times St, and Rt is equal to beta times Rt minus 1 plus 1 minus beta times Wt is W. So this is your RMS prop. 1 second. I've used this ST, but wait, let me just check the RMS prop once. Beta times this plus 1 minus beta times this. I guess C is your cost. This is the gradient, right? Okay, so this is not there. So this is your RMS prop. Which of the following is correct property of RMS prop optimizer? RMS prop divides the learning rate by an exponentially decaying average of squared gradients. So that you can sort of see, I guess. If you take R0 equal to 0, then R1 is beta time, 0, 1 minus beta into G1. Let me just consider it for some, like, just assume it is for one parameter. R2 is beta into 1 minus beta G1 square to 1 minus beta G2 square. R3 is beta square into 1 minus beta G1 square so some RT will be summation beta power T minus 1 into 1 minus beta T minus tau. So for R3 I will get 3 minus, is there a plus 1? So you can see this is the options are, it is a learning rate by an exponentially decaying average of squared gradients. So is this an exponentially decaying average of squared gradients? So you have R3 and it is, you have exponential terms as weights to these gradients and they are averaged based on this exponential sort of weights. So it is an exponentially decaying, right? Because beta square is like as you move back in time, beta square will, like beta power t will be very small value. So I guess it is a is dividing the learning rate by an exponentially decaying average of squared gradients. So what I meant was, for you are at currently at t, but you sum the gradients from tau equal to 1 to the current time step t, and you are weighing them by this exponential of beta. For when you are summing for tau equal to 1, it is beta power, it should have been tau here, beta power t minus tau. So in the first term, if you see, this is multiplied by this only. Then the second term, they multiplied the gradient at first time step with beta, then with beta square. In the third, the first time step will be multiplied with beta cube. Like that, it will keep on increasing exponentially. But the beta term, because it is less than 0, so it will decrease exponentially. Okay. So let me just look at the last question. Which of the following represents the contour plot of the function f of xy equal to x square minus y? So that means we have to look at what values this has constant sort of thing. So at x equal to 0, y equal to 0, it is 0. That is quite evident. And if you see, when y equal to x square, I think we should look at those sort of terms, y equal to x square. So you have quadratic functions at which it will be 0. So at 0 minus 4, it is not 4. 0 minus 4, it is 4, yeah. But when x is, or when y is 0 and x is minus 4, it can't be minus 4. So at minus 2 point something, it can x square can be close to some 5. So basically what you will have is for different values of f of xy, f of xy equal to 5, then you have x square minus y minus 5 equal to 0. That will be this plot, I guess. And you have x at f of xy equal to 0, you have x square minus y equal to 0. That will be this plot. So what the contour plot represents is uh, the parts of the plot, the values of xy for which the f of xy value remains the same. So at all these points of x comma y, f of xy is equal to 0. For all these points, f of xy equal to 5. For all these points, f of xy is equal to 10. So the correct answer is this B option. Well, this is a quadratic sort of equation, and you have this quadratic contour plots here. For other values, like here you have a straight line, so it can't be. Here you have concentric circles, that also cannot be. Here also you have some sort of a symmetric thing, that also cannot be. So that is all the questions I had for today. So I'll stop this part now. This time is also up.